Hi there, students. This is Dr. John, your physics and math professor, and today we're doing another problem with regard to forces and boxes and friction and all that sort of stuff. So hopefully this problem gives you a lot of introduction to these kinds of issues. So here we have somebody pushing these two boxes. The boxes are right against each other. Box number one is where this person is pushing with a force of 730 newtons. And box one is pushing box two, and they're moving along like this. They start off from rest. We're supposed to find the acceleration of this system, and then we're supposed to find the force that box one pushes on box two with. Now this is a multi-step problem. Let's just do it one step at a time. So over here I've redrawn these boxes, really tiny, with the different forces. The green force is the force you're pushing. This red force is the force of friction. If you remember from some of our other problems, we calculate the force of friction equals the normal force times mu. So when these boxes are sitting on the surface, they're obviously pressing down on the surface, and the surface is pushing up on them with an equal force. That force that's pushing up on them is the normal force. The normal force is just the force that's perpendicular to the surface. The word normal in physics means perpendicular, or in mathematics. So we're going to be looking at the normal forces here. We're going to be using Newton's three laws. Just to review them for you really quickly, you don't have to memorize these three laws, not word for word, but just understand the concept. So the first law is sort of the law of inertia. That is, if something is sitting still or something is moving at a constant velocity, unless there's unbalanced forces acting on it. What I mean by unbalanced forces is, let's say there's a force pushing it to the left and a force pushing it to the right. If those forces are the same, it's going to continue to move. Those are balanced forces. So there have to be an unbalanced force or a net force pushing in some direction. If there's no unbalanced force, no net force, the object will continue to move or will continue to sit still. That's Newton's first law. And then he wrote the second law, which expanded upon that. He says, what if there is a net force? So this F here is the net force, which is sometimes called the net force or the unbalanced force or the sum of all forces. Sometimes they'll do something like that, the sum of all forces. So the net force is going to cause what? It's going to cause the mass to accelerate in this way. The force is equal to the mass times acceleration. In other words, the heavier the mass, the less the acceleration. A very simple conclusion, but very profound and has so many applications. That's the second law. The third law is that if there's a force pushing something, the other thing is going to be pushing back at it with the same force. So if I'm pushing on the whiteboard here like this, the whiteboard's pushing back on me with the same force. This marker that I'm holding between my fingers, I'm pushing inward on it with my fingers. It's pushing outward on my fingers with the same force. So this is something that we're going to be using a lot in all of our problems. It's very foundational to everything that we do. So what we want to do is we want to find the acceleration of these two boxes. So what I've drawn up for you here is a number of different forces. The green force is the force pushing it. The red force is the force of friction. As I just mentioned, of course, they have gravity, mg, pulling it downward, whatever the mass is, the mass of one box or the other or both. N is the normal force, which in this case is going to have to be equal to this, have to be equal to mg, because there's no other force. It's not moving up and down. So this here is going to have to be equal to mg, whichever m we're using. So I did a bunch of calculations for you here just to save us some time. I looked at the normal force for each of these, and I says each of these boxes is going to have a normal force. The normal force for box 1, N1, is going to be 75. That's its mass, times 9.8 gravity, which is going to be equal to 735 newtons. I just did this quickly. We'll save ourselves a little bit of time. Box 2, the normal force is 110, 9.8, which is a little over 1,000. I didn't worry about significant figures. Here we have 2, here we have 2, here we have 2, here we have 2. We're going to do the two significant figures right at the end, but for now we'll just keep a couple of extra so that we don't have a lot of rounding areas. And then I did the normal force for both of them combined, 1 and 2 combined, just adding up their weight. Their weight, of course, is 75 plus 110, 185. Multiply that by 9.8, the acceleration of gravity, and I get this value over here. And then what I did is this. Since this is the normal force pushing upward here, this is N here, right here, this mauve color here. Then I did, as I said, let's find the force of friction that this would create. The force of friction would be the normal force times mu. So I multiplied those all out, just simply took 0.15 and multiplied by the normal force to get various different values of the force of friction. Box number 1, box number 2 has a little more because it's a little heavier. Both of them together have a force of friction that basically adds these two up. So here we've calculated the force of friction, which is going to be very useful for our motion. Now, when we're calculating the motion of something, the acceleration of something, what we need to do is we need to figure out the net force. let me do that right here in this little spot. So the net force, or the sum of all forces, if you want to put it that way, we have this green force to the right of 730. So that's 730 there. And then there's a force to the left. The force of friction always opposes the desired motion. So if you're trying to push it in this direction, friction will try to push it back in the other direction. And friction will never exceed this force here, because friction's not going to suddenly make it move spontaneously in that direction. It's only going to be effective when you're trying to push in this direction. So you're trying to push in this direction, friction is going to try to hold it. Friction may exceed this value. That means you won't actually be able to move it. But once you start moving it, of course, friction is going to have to be less than this value, which is what we're looking at in this case. So 730, notice friction is much less than 730. And what we're looking at here right now is we're looking at both these boxes together. We're looking at all the forces that go outside of these two boxes. The normal force sort of goes outside, mg goes outside, friction goes this way, and the force applied goes this way. So the net forces would be left and right. To the right, it's 730, and to the left, or slowing it down, reducing the motion, is 271.9. I've got way too many figures there. Let me just make this 272, just for fun, minus 272. And let's calculate what that difference is. It's about 500, a little less than 500. Let me just check on my calculator. So here, 458 is the net force, or all the forces added up together. That's the force that we have left. And what is it that those forces are accelerating? They're accelerating both these masses. So if we want to find out the acceleration of both these masses, because they're going to stick together here, is we're going to have to take this force and this mass here. Remember, we have just simply force is equal to mass times acceleration. We want to find the acceleration, so we divide both sides by mass like this. So the acceleration is equal to the force divided by the mass, which in this case is 458, divided by the total mass. We've already figured that out over here, 185. And that's going to be about 3. Let me just check my calculator. I am getting 2.48 meters per second squared. Let's write that up here. The acceleration of this system here is equal to 2.48 meters per second squared. That's the acceleration of both the boxes tied together. So now we found out this, if that's the acceleration of box 1, that's also the acceleration of box 2. So what is it that causes box 2 to accelerate? I'm going to erase a couple of things here and then come back, and we're going to try to find the force that box 1 has on box 2. So here I've erased a couple of things, and we're going to be focusing right now in on box number 2. Notice I've drawn a little dashed line around box number 2. We're trying to find the force that box 1 pushes on box 2 with, which I'll call F12. Now, the net force acting on box 2 is going to have to be equal to the mass of box 2 times the acceleration. And box 2 is accelerating with the same acceleration. Now we're just dealing with box 2. So whatever net forces acting here, obviously up and down, are going to be equal. So we're not worried about those. But whatever net forces are, which is going to be these two things. It's going to be the force acting on box 2 from box 1 minus the force of friction. So whatever force is acting on box 2 from 1, that's F12, I've written that right here, minus the frictional force. This takes into account the direction. So now frictional force is positive, is going to be equal to the net force. This is going to be the sum of all the forces, and it's going to be positive in this direction because the thing is accelerating. So that's going to be equal to the net force, or the mass times acceleration. Well, the mass times acceleration is this, 110 times 2.48. And that's going to have to be equal to this thing here. We don't know what that is. F12 minus the force of friction, box 2. We've already done some calculations here. Box 2, the force of friction was 161.70. Let's just keep 3 significant figures. That's still one more than we were given originally, and that would be 162. So that's going to be subtracting 162. This, of course, is going to go to this other side, because the force that's acting on box 2 is going to have to exceed the force needed to accelerate by the friction. You're going to have compensate for the frictional force as well. So let's just do this calculation here really quickly. Here, for this calculation, I got 273. Again, I've rounded to 3 significant figures, and we'll want F12. So I could take this to this side. Are you okay with that? Make this a positive over here. So I've taken this to this side. All of this together will be equal to F12. on 2. Let me erase a couple of things here so I can do this calculation. Now we have the force box 1 has on box 2 is equal to this plus this. 435, that plus that plus that. Looks right. 435 newtons. So that's the force box 1 has on box 2. Let's just do everything now to 3 significant figures. So this here to 2 significant figures, would be 2.5 meters per second squared. That would be your significant figure answer. And this one would be 440 newtons to 2 significant figures. So let's just take a look at our answer here. The force that's acting on both boxes is 730. The force that's acting just on box 2 is 440. That's considerably less. It's about half of that. And this weight here is about, a little less than half of the total. So that sort of makes sense. It's in the right region. Always ask yourself if your answer makes sense. So, and we've rounded both of these off to 2 significant figures. So I think we've done a good job with this problem. I hope this helped. If it did, like and subscribe, and I will see you in the next video. Bye-bye.